Welcome everybody to Sustainable River Basin Management, part 2 of module 2, second week. Today we will be speaking about stream morphology, and I want to demonstrate you some of the basics of science-based approaches to stream restoration. Let's first talk about river characteristics. And remember what we have been saying when I introduced river systems as such. The river characteristics are described by the physical, the chemical, biological properties of water and the catchment in which this water appears. It is shaped by human and natural activities, and the stream characteristics reflect the complexity of our river system. We can differentiate between natural river systems, just an example here, although it may be shaped by our use of the forests before, or the use of water somewhere upstream. It appears to us as natural. And then what we can call constructed, and this constructed could be due to our human interventions. It could also be due to animals shaping and constructing river streams, parts of the stream. For instance, beavers. An example of how we humans construct and still perceive rivers as nice or beautiful or appealing is shown here. We can usually describe rivers being in equilibrium or being in non-equilibrium. And what we mean by this, we want to discuss now. Rivers are in a balance or steady state or imbalance between their erosion rate and the deposition rate. So we are speaking of the removal of sediments and the deposition of sediments at somewhere else. This figure here shows us a model of a river. You could see the river source somewhere here, the watershed boundary or the catchment boundary here, and then the course of the river along this profile, this surface, and reaching the sea eventually, the ocean. So the sea level usually is our base level. That is the lowest level to which erosion can take place and to which sediments can be carried and transported and deposited. So when we speak of equilibrium, we mean that our profile would look like this, and we have reached a stable state where both erosion rate and deposition rate are in a balance. We can identify such river systems being in an equilibrium state by their concave up shape of the longitudinal profile, this one here. However, as you may imagine, most of the rivers are not in equilibrium. So we speak of a dynamic equilibrium instead, which also is a description of the self-regulating capacity of the streams to adjust to changes. And those changes may be in flow rate or in sediment volumes. And we speak then of a steady state instead of an equilibrium as such. Most of our rivers are in a steady state equilibrium. Let's look into the river profiles, and you are familiar with a usual division that we use also for water management purposes. We speak of an upper course, we speak of a middle course, and the lower course. The upper course is where our source areas are of the water, our springs, where maybe most of the rainfall occurs, somewhere in an upland area. And then we have our middle course where we have slower velocities, we have less steep slopes in our profile. We may have higher water volumes overall, and then we reach our low courses where most of the deposition takes place, where we will observe our floodplains, and eventually our water will join the ocean, and by that will have reached its base level. Now, this base level can shift, as you know yourself that sea levels have been rising and decreasing over the geological timescales, and by that we influence the dynamics of this profile. We can identify for each of these sections of our river system according vertical or valley cross sections, and in the upper parts where we have steeper slopes and higher energies, higher velocities, stream velocities, we usually will see a V-shaped valley where primarily vertical erosion will shape and dominate the landscape and the evolution of such a valley. In the middle course, we probably will observe more widening. We will see wide, vast valleys, and what is most prominent is lateral erosion taking place along the flanks of the river valley. And in the lower courses, we will observe more of the deposition of these fluvial sediments and a refilling of the level of the floodplain level. So our valley slopes are therefore a good measure of sediment transport rates, and those sediment transport rates are influenced by the slope, the amount of water discharge, and the sediment size. So we can use all of these as indicators of where we are in a river profile, if you can see only a part of it from a satellite image, for instance, and we can draw conclusions on what type of river system we are in from some of these properties. Now, this is not stable as such. The base level is changing. Our sea levels are rising at the moment. Our continents are not stable. They are uplifting in many cases as a result of the ice age. So there's a progressive head erosion taking place, there's denudation taking place. So this point is shifting, and more of the land that is not currently part of the water catchment will essentially be caught and involved into one river system, expanding that watershed and changing slopes and velocities and erosion again here. Base level changes are very important, and we will be talking about this throughout this class and the next class as well. It's essentially a relationship between slope and catchment area, which we can use as a measure of equilibrium state. Now, equilibrium meaning with regard to mean sea level, and we've been saying that this is changing. So the river can, however, adjust its own river profile to a local base level. And what such a local base level could be is, for instance, a lake, a water reservoir, a surface where water surface where flow velocities are slowed down to such a level that that sedimentation will be, or sediments will be trapped in this part, and if there is an overflow, again we will have the formation of a new slope and a new river profile downstream of this lake system down to the next base level. That base level could be again a lake or a dam, it could be the final destination, it could be the ocean. Now this shows us here, this line here shows us what the natural, so to say, natural profile of this river would be, and here we see what it is as a result of a lake, which could be a natural lake or it could be a man-made reservoir. Now this is very important, and we can we see how deep we already influence our hydrological processes by simply adding such a new base level to a landscape. Now we usually talk about Knickpoints or convex segments occurring in river profile, and those indicate disequilibrium in a river. And those could be the result of tectonic events, they could be the result of base level changes, or they could be the result of some lithological perturbations. And I found an interesting example which I want to present to you here. You have a region in Middle Europe at the border of Germany and Czech Republic, and river systems draining from south towards the north here, and we have a major graben structure here in this area, the Egergraben or Eger rift system. Now the red dots here indicate such Knickpoints which were identified by remote sensing techniques and by analyzing river profiles. So we have 1, 2, 3, 4 rivers here, and the same shown here in this map, and you can see clearly here where these Knickpoints occur, where such change in the profile occur, and we can see here, or projections were made from in this publication, this work, what the natural profile should have been if not a specific event would have come and disturbed these natural processes. And in this case, it's mostly tectonic events, because we also go quite back into our geological history, and we can link it to specific tectonic phases, evolutions of this mountain area, and the rift area that I mentioned earlier. So this is one way of analyzing the evolution of rivers, but also the geological history of certain areas in combination with remote sensing techniques. Now let's focus on the controls of channel morphology. What influences it? Most of all, it's geology, or the type of soils that we have in a certain terrain. And what we mean by that is mostly the strength of a rock, how resistant this rock is to erosion. And just an example here, the Victoria Falls of one of the major rivers, the Zambezi River. You see this huge stream, which then has been interrupted by a major fault, or several faults here, and which have shifted rocks of differing strengths next to each other, and for that reason created a differential erosion and Falls were the results, the Victoria Falls were the results of that. You can also see on one side a very greenish, very wet zone, whereas on the other side of this riverbank you see a very dry area, which also indicates quite some influence of faults and tectonic features in influencing hydrology here. The second important control element of morphology is the rainfall, precipitation, and the transformation of that precipitation into flows. That could be in terms of magnitude, it could be in terms of duration, and in terms of frequency. We come back to this. And it includes all of the different flows, our groundwater, surface water, that linkage between groundwater and surface water, our base flows, our low flows, our flood and storm flows, and the maximum floods occurring in such a system. In addition to these already mentioned primary, very important controls, ecosystems are very important. The flora, in terms of from very small, from micro to mega, and fauna from micro to mega. And let's just take an example here of a floodplain region. And you can see here drainages where water joins the major stream, major canal here. And you can, in many cases, those are preferential drainages because wildlife uses those as the shortest lines to access the main river or main canal, to cross or to get to the source of water or get to the water as such. So elephants or buffalo or large herbivores, hippopotamo, use those, and by using them all the time, they increase the drainage, and they also may even create connecting drainages between some secondary or some other stream channels far apart from the main channel here. So they are quite important in shaping the drainage and shaping the landscape. And then, of course, humans and we shape the morphology and have influence on our river systems. The substrate, the rock, or the alluvium or colluvium, the soil that occurs at the bottom of our streams, is quite important. And lastly, the sediment budget, what is available, what enters the system, what leaves the system. As an example here, an extreme, we have two rivers joining, this river joining another large one, and this tributary here brings a lot of sediment, and quite some time those two water masses are not able to mix, and this has quite substantial impacts on the aquatic life, but also on the flow patterns. The velocities will slow down here, more sedimentation will take place in this area. You may have more bottom erosion taking place due to this dense flow of suspension in this mainstream. So there are various processes influencing this. Yet another channel morphology control is the geometrics. We come back to this. The channel gradient slopes, we talked about this, and constrictions on, for instance, the lateral migration. And then we have some other factors which we sometimes think are much more relevant, but are actually more underlying and secondary. Those could be short-term geophysical or tectonic events, some displacement of geological layers as a result of earthquakes or uplift or subsidence. Or it could be water chemistry processes, such as karst features forming such large caves, openings where rivers increase the chemical processes which have formed this as a small space. So important is on the flow systems, the flow capacity as such, and that develops under the influence of long-term frequent low magnitude flows on one hand side, and as a result of high magnitude short-term and usually less frequent flows. And those high magnitude events can very often undo the processes which were shaped under these low flow conditions. And this is very important to keep in mind. Now, we observe high flow channels which accommodate large volumes of water, which are shaped by stronger and infrequent storm flows and usually cause a lot of sediment movement, sediment erosion, transportation and redeposition, and as such really shape and rearrange vegetation and landscapes. So those are very important events in terms of landscape changes. An example here of the Missouri River, this is a satellite image. You see different land uses taking place here, some agricultural large fields here, and we have the Missouri River Valley here. This is the low flow channel here, but you also can see here a wider valley which corresponds to this high flow channel. We see that those river floodplains are used very much for agriculture, very important, very fertile zones. And then we have on the other side the same part here, this river which is dry on this image here, now carries water as a tributary, and we see that this entire high flow channel is filled with water. All of these agricultural fields are underwater in this image. So this is has a major impact on and demonstrates these major forces executed by such high flows. Now let's look into the precipitation and transformation into flows. And we can see that most of the river channels have capacity to accommodate all those different flows. They have usually the capacity to accommodate two different types of low flows, and they have the space, the capacity to accommodate moderate and high flows. Just an example here, one of the rivers in southern Africa here, the Save River, coming from Zimbabwe. And here, this is the low flow, one of the low flow channels here. This entire part is part of the low flow to moderate. This channel can migrate, it can move, can be 1 year here or somewhere closer to this bank here. It could be somewhere here. It could split and be distributed. So this is changing very much. And then we have this sand part here, which will be the active part under moderate flows. And then we have a river bank here, which you can see here, where this riparian vegetation starts, which will be active under high flow conditions. And then we may have extreme events which may even go above bank flow here and spill over. Now, having said this, let's look into the stream geometrics and the velocity. And this is an interesting example of an outdoor laboratory at the University of Minnesota. And you see a person here as a scale, and they use that to analyze the impacts of stream geometrics on different interventions and give inputs to stream restoration interventions. And here we have that same stretch here and a measurement of the velocity magnitudes in meter per second. And we see that this starts from a blue, no flow, to a purple, whitish, where we have higher flows reaching, in this case, about 22 meters per second. And what we can see here, that in a river bend, those bending, the curves here very much influence flow velocities. So we can expect sedimentation to take place in areas where the energy is low, velocity is low, where sediments can be deposited, and we can expect certain grain sizes here, probably the smaller particle sizes being deposited here, whereas in those parts where our stream channel is more straight or more narrow, we can observe higher velocities, which will allow only larger sediment particles to settle or deposit, or in most cases probably will remove larger particles and drag them along and deposit them in some other downstream area. So those scientific approaches are very important to define interventions, how we shape a river, where should be boulders, where should be, how should the banks and the lateral parts of a river be shaped to achieve what we want with our intervention. Now, let's continue on in-stream channel geometries. Dig from the outside into what happens inside a stream channel itself. And that classification which is most commonly used is based on the geomorphic characteristics and physical processes. And those are used for stream restoration and also for stream management actions. So we may use different classification schemes for different purposes. So keep this in mind. This is not the only one existing and not the only one which you may find useful for your specific applications. Those are the most basic schemes of in-stream morphologies. We may have those large boulders here. We may have boulders and pools where the velocities may slow down. Also, temperatures may increase here and allow for different processes to take place. There may be a spillover into the next and so on, cascading or stepwise movement. You may have inclined but pebble size sediments on the bottom. We may have some riffle structure, large riffles here, which also slow down velocity and may foster sedimentation, may create deeper parts and more shallow parts, which could be penetrated better by light, or some others may have lower temperatures and more oxygen may be placed into the water due to those effects. And we may have something like this where we have changing flow velocities and high velocities shaping the bottom like this. So those are basic classifications, and we may use those actually to place such features and create such features artificially to achieve certain benefits for our water system. Let's look into the qualitative properties of these equilibrium channels. And let's recap that the channels are formed as a result of the water discharge, the amount of water, the valley slope, and sediment sizes. There are many different schemes again and classifications, and I'm just showing you one here, which shows us here the adjustment stages in channels and the different cross sections which are typical for these stages associated with certain slopes, more shallow or plain, almost not existing slope, and steeper slopes here, and how the plane view of these rivers will look like if you, for instance, take an aerial picture or a satellite image to look into this. So we can see that there's a process which starts from a very curvy, very pronounced sinuosity towards a straightening, widening, and then coming back to an old developed wide channel within which we again have a very curved and very sinuous shape of river in a floodplain, for instance. So this is could be a mountain area, a headwater, and this could be a floodplain. And now, what are the parameters that we use to analyze those properties? We look into the drainage area, how big it is. When it is very small, we usually can assume that it's a young river system. We may look into the channel widths. We may use the channel depths, just like here in this ratio here, as a description of typical river systems. We may look into the sinuosity, the radius of curvature, and we may use the slope of the river. So those are some of the approaches, and not all may be in all cases appropriate, but we can use them to characterize entire countries or regions. Now let's look into, as the last one today, into the sediment transport and loads, which we have not talked about yet, and I just want to show you the different ways in which sediments can be transported and or loads can be transported. So we have our water here and we have our riverbed here, and what we've seen in one of the pictures earlier was a suspension where sediments are occurring in very fine particles which take very long time to settle, to deposit somewhere. So they are usually carried in suspension along the flow of a river. Contrary to suspensions, we have also solutions. This means that minerals or particles or chemicals are chemical elements are dissolved in in the water in the form of ions, and in that way carried within the water to some other places where maybe due to evaporation they may precipitate again and form minerals again. And then we have different sizes of larger particles, of sediments, of boulders, of sands, of pebbles, which depending on the flow velocity would be able to be tracked along, to roll along or spin along, and by that way erode the surface of the riverbed. They may form water mills, for instance, deep holes here, for instance, or such rocks could be jumping, flow energy, kinetic energy may be accumulating here, and after some time these pebbles could jump and change their position, could this call siltation, and be tracked along the riverbed and deposited. By changing the velocity here, you can imagine that those processes change here, and those large boulders may be easily moved and deposited somewhere else under extreme conditions. We will stop here, and I see you next time again. Thank you.